Hi. Yes. Hmm? Oh, because we haven't written any tests yet, and there hasn't been any enriched work yet. Yeah. Okay. Let's talk about what all of your quizzes are next week. Okay, so let's talk about what all of your quizzes are next week. Oh, you did not get that. Okay, hang on. I have that somewhere. Where did I put them all? Oh, that's the wrong block. It's not going to be helpful. Let's see where I put this block. There. There you are. Oh, that doesn't sound good. Why is it making that horrendous noise?
That's much more control.
Okay.
Did you look at the name of that? I know.
Okay. So Monday. Let's make this bigger so maybe you can see it. I mean, I can't make them much harder because, like,
It's the same material.
what else can I?
For example, syntax.
Yeah.
You can make it more challenging and more
Like, how could I? Like, I've already given you all the weird stuff. Okay. This. Shh. Just so you guys are clear, this unit that we're doing right now is like the easiest unit. Okay. So you can expect your grade after Unit 1 to probably be the best it's going to be all year because it only gets harder. Okay. So if you're like, yes, I'm getting, I didn't have to study and I got, 90%. That's great. I can just keep not studying and I can get 90%. That's not going to work because the rest of it progressively gets more and more and more difficult as we add more and more and more levels. Not everything. I mean, we do go back to let's do a quick review of how to name compounds, which you've done in grade 9 and 10. So hopefully that will be really easy. Hi. Yeah, for sure. Okay, so on Monday, February the 11th, that is next Monday, there will be a quiz on scientific notation and metric prefixes. So this is in our channel that says upcoming quizzes and tests. So if you want to see all of this, you can go to that channel. The metric prefixes, we are going to review that right now so that you will know it. Let's go here. And you could write this down maybe even on your little progress report if you want to. Right? Just so that you feel good about this. What did I do with my glove? My glove is gone. Oh, well, that's okay. Oh, there it is. So for this part of the quiz, you will need to write the name, the abbreviation, and the power of 10 for all of the metric prefixes. And to remind you of those, we are going to sing the song. All right. I'm going to write down. You can write down along with me. So we start with mega, kilo, deci, centi, milli, micro, nano. And so you need to be able to write those out. And then you need to be able to write the symbols, mega, kilo, deci, centi, milli, micro, nano. Now, if you want to know it really well for Monday, you're going to join in, at least mouth the words so that your brain is thinking that you're saying them. Mega, kilo, deci, centi, milli, micro, nano. 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 Now, that's all well and good. We also need to know the powers of 10, right? So, we're going to put our powers of 10 over here. Okay, so we're going to start with mega, kilo, deci, centi, milli, micro, nano. 6, 3, 1, 2, 3, 6. 9 is for the nano. Mega, kilo, deci, centi, milli, micro, nano. 6, 3, 1, 2, 3, 6. 9 is for the nano. Everybody, mega, kilo, deci, centi, milli, micro, nano. 6, 3, 1, 2, 3, 6. 9 is for the nano. And now we'll do it one more time with a blank slate here. Mega, kilo, everyone. Deci, centi, milli, micro, nano. 6, 3, 1, 2, 3, 6. 9 is for the nano. All right, now remember these are all powers of 10. And the first two are positive or negative. First two are positive and the rest of them are negative exponents. All right, so you can just go through and do. There you go. All right, so in the end, what it would look like on the quiz is that you would have this, and you would have this, and you would have this. Okay, with all of your negatives and whatever. And then next unit, we will be using those as conversion factors when we are doing unit conversions. All right, so there is where we are at. All right. Now, what else is on the quiz on Monday? Scientific notation, okay? So for this one, you should be able to convert from scientific notation to standard notation or from standard to scientific notation. You should be able to keep the sig figs consistent. So if in standard notation it has 3 sig figs, in scientific notation you should make it have 3 sig figs. If in scientific notation it has 6 sig figs, in standard notation it should have 6 sig figs. You should know what an overbar is and how it is used. So remember the overbar only on 0, right? Not if there is a decimal in the number. Not a decimal in the number. And it shows you the uncertain digit. It tells you the last sig fig. Okay, because that's going to be, it's not like a huge important part of it, but sometimes in order, especially when going from scientific to standard, if you want to keep the sig figs the same, you'll have to use an overbar. Okay? There we go. You should know the 3 requirements for a number to be in scientific notation. Now, quite frankly, as long as you know the first one and you understand it, the other 2 are just saying the same thing in different ways. You need a single number 1 through 9 in front of the decimal. No more, no less. Okay, which also means you should not have a 0 because it's not a 1 through 9. And you should not have 2 or more digits in front of the decimal because that would give you more than a single digit. That would give you more than 9. It would be 10 or 12 or something like that. Yes? So a single digit in front of the decimal that is not 0. Also, you should be able to recognize a number that is not in scientific notation. So that would be our no-no notation, okay? That would be where you have a 0 in front of the decimal or where you have 3 digits in front of the decimal. And when you're given something like that, you should be able to change it into scientific notation, okay? So recognize that it's not in scientific notation, change it into scientific notation. And I have not yet put in here which pages this is on, but I will throw that up in your homework and on here, so it is there for the weekend. I'll put it both places so that you can look either place and find it, because I know it's hard to find things sometimes. Okay? So that's Monday. Tuesday, we have a quiz on algebra and units. That's what we did yesterday. Solve the equation for a variable, and then find the units for that variable. Yes? And where are you going to find practice for that? You can find practice on pages 100 to 104 in our workbook. You can find practice in Hebden, which if you want to sign out a copy, they are on the back counter there. If you don't want to sign out a copy, I have a note here telling me to make sure that I upload Hebden before I leave today so that it is on Teams. Okay, so I will put it in the normal, let's see. So in our normal thing, we would have our general channel. So we would go to general, and then there would be files. And right now it says Unit 1, Unit 2. There's going to be something that says Hebden, okay? And it will be in the Hebden file, okay? All right, back to here. And upcoming quizzes and tests. Plus, make it bigger, make it bigger. I wish you could just zoom like everything else, but that's okay. Okay, there we go. Okay. Algebra and units, be able to solve the equation for a particular variable and be able to substitute the units into the equation to find the unit of a particular variable. So there's an extra practice on that you can work on over the weekend. Practice pages 127 to 131, but like I said, I will throw that into the homework as well so that it's wherever you want to look for it, okay? So those are our quizzes. And I think I said we would have our test on Thursday, but I realized the reason I did not want it on Friday is I felt it was too long. Friday classes are a little bit shorter. But then I thought, hey, we haven't done the solution lab, which has a lot of like sort of stuff that would have been on the test. So the test is going to be shorter, and therefore we can write it during a shorter class period. Yes? All right. So I've moved it to Friday, so you have just a little bit of extra time. You know, if you discover on Tuesday that you didn't understand whatever we had a quiz on Tuesday, you have a couple of days to sort yourselves out on that. Okay? So Unit 1 test is going to be everything you've written a quiz on. So quantities and units and metric prefixes, accuracy and precision, counting sig figs, identifying the uncertain digit, scientific notation, exact and inexact numbers, all the vocabulary, and I'm going to make sure that I've updated this because I just copied this from last year, so I will update the vocab list, all right, and provide you guys with a vocab list. So if this weekend you're like, I'm going to update my little flashcards or my vocab list, you can do that, okay? So that's everything there, all right. Good. So I'm going to close that now. And we are going to go to 1.3b. The solutions video. We already saw one video on solutions. We're going to watch a second one. I think actually what might make sense, last block I did it, we filled it in as we went. I think we'll just watch it through and then we'll fill it in together. Okay. We'll see if that works better. I don't know. Yes. What's up? Huh? What's that? Vocabulary? I said I'm going to upload it.
It's not there yet.
No, it's not there yet. Okay. Which one is oh, so we would call the sugar the what? The sugar would be the sol. Is it the solute or is it the solvent? The sugar is the solute. Sugar is the solute, water is the solvent. So when they say spread out uniformly, that means evenly, okay? What is kinetic energy? Kinetic energy is the energy of movement. So if we stir it, what are we doing to the kinetic energy? We are increasing the kinetic energy. We're making the particles move faster. So they're all spread out evenly. What kind of a mixture is it if all of the particles have spread out evenly? Starts with an H. Yes. Homogeneous or homogeneous. Either way you say it is good. Okay, why is it not playing? There we go. Okay, so I actually did this little demonstration. I did not stir this at all with my last class. So I added the drop and I just let it sit there. And what happened? It all diffused out and eventually it ended up being evenly distributed. Okay, but you can speed that process up by stirring it. So the yellow molecules, the yellow marbles are the sugar. Okay, yellow is the sugar. What do you think the blue is?
Water.
Blue is water. And what do you think is going to happen if we start shaking this tray that the stuff is on? Yes? The yellow is going to spread out. All right, and we will end up with what kind of distribution? Homogeneous, uniform, even. Okay? It's all going to spread out randomly. Let's watch it happen. Right? You can see what has happened. Do we have a relatively uniform, or sorry, relatively spread out, evenly distributed thing? Yeah. The reason you might still see clumps from time to time is that we don't actually have very many particles, right? There might be 100 marbles here at most, okay? And in reality, the number of particles is going to be like 600 hexillion, yes? So you're going to be like, okay, just because there's 3 clumped together, that's not really a clump. That's just, 3 random things kind of getting together. Okay, so if we were to count all of the sugar molecules on the left, it would be about the same as the sugar molecules on the right. And if it's not exactly the same, if you were to continue to shake it, it would, and take a photo at any given moment, it would average out so that it would be the same. So if you took a picture right now, we actually did count it in the last block. There were 13 on this, 13 sugar molecules and 17. Okay, but if you shook it some more, maybe next time there would be 17 and 13, or maybe there would be 15 and 15, right? So it would even out over time so that you would get an average on each side that is the same. That is called diffusion and dissolving, okay? When the free and random motion of molecules. So that's what's going to happen either next week or the week after, whenever we have time to do the lab. Okay, we're going to be making a solution, and we will be putting the solute into the solvent. That's because water dissolves everything in the universe. No, I'm kidding. It doesn't dissolve everything in the universe, but it is the best at dissolving the most number of things. Any other liquid that you have is not as good. It won't dissolve as many things as water. Okay, water is particularly good at dissolving things because it has very strong intermolecular forces that can grab onto other little molecules and pull them away from each other. We'll talk about that in just a little bit. Okay. Would this pen dissolve in water? No, not everything dissolves in water. Okay. And in fact, the solute that we will be using in our lab is not very soluble in water. We're actually going to have to heat it to get enough of it to dissolve to make a real solution. Okay, that means we get to play with Bunsen burners and stirring things and thermometers. So it's a little bit of an exciting lab. All right, we get to do a lot of nice techniques. We get to filter. It's very cool. Okay. Is the Alka-Seltzer the solvent or the solute? Solute. Good. But yeah, it's totally fine. You could have the solute there and then you could add the solvent. No worries. We actually do that when we're making a solution from scratch. Like a salt solution from scratch. We'll do that this year, making different concentrations of solutions. Okay, and that's it for that. I did want to just pull up a little video of salt dissolving in water, so you can just take a look at why water is kind of good at dissolving things. So water is actually, maybe I'll do it on here so it is on the recording if anyone's away. Water is a polar molecule. What that means is that it has a positive pole or end, and it has a negative pole or end. And in the case of water, the oxygen end is somewhat negative, and the hydrogen ends are somewhat positive. Now, what do you guys know about positive and negative charges? Positive and negative attract. So the fact that many other substances also have charges allows the water molecules to be like, ooh, I see a negative charge. The little water molecule will go, ooh, negative. I will grab you with the positive hydrogens and rip you away. All right, and we're going to watch like a little video of that right now. Okay, salt dissolving in water. There we go. The music at the beginning is really loud and then there's no sound. There's our little water molecule. There's our salt. Now, here's a question for you. Do you recognize this structure here? Starts with a C. Ooh, it's a what?
Crystal lattice.
It is a crystal lattice. Do you remember this? Do you remember this thing? You might not have been here when we did this lesson. Yeah, so ionic crystals exist as crystal lattices. Positive, negative, positive, negative, positive, negative.
She went over it.
What kind of a compound is this? Is it covalent? Is it ionic? This is salt. So we've got a positive and a negative. and a positive and a negative. And if this is a positive particle, what do we call an atom that has a positive charge? We call it an ion. So if I have a positive ion and I have an atom that has a negative charge, that's another ion, what kind of compound would this be? If it's made of ions, what kind of compound is it? It is an ionic compound, okay? Ionic compounds exist as crystal lattices. They do not exist as molecules. Okay, molecules are for covalent compounds. All right? So our waters are little molecules, but they do have this positive and negative end. And remember that the salt has positive and negative ions in it. And let's look at what happens with these. Okay, you can see the red is positive and the blue is negative. Similarly, in our crystal, the sodium is red, positive, and the chloride is blue, negative. Which end of the waters are pointing towards this chloride ion here? Which end of the water? The red end. Yes? So the positive end of the water is, red positive end of the water is pointing towards the blue negative chloride ion. Okay? And it's pulling on it because positive pulls on negative, and it will actually pull it away from the other ions. Okay, so watch that happen. Here it goes. Woo. And then, same thing is going to happen, but now it is the negative oxygens pointing towards the positive ion, and they're going to pull it away. Woo. Off it goes. And finally, if you look at the way the water surrounds it, what do you notice? Here we have our blue negative ion. What's pointing towards it?
Red.
The reds. All of the hydrogens are pointing towards the negative chloride. Whereas over here, we have the red ion in the middle, the positive ion. What's pointing towards it?
Blue.
The blue negative end of the water is all pointing towards it. Okay? Now, all of these forces, there are forces between water molecules, and there are forces between water and ions. And we're going to just write that down because, again, I've got stuff up here that I want to make sure is recorded for us. So we have, if I have a water molecule where I have positive, positive, negative, and I have another water molecule, which is positive, positive, negative, what will this water molecule here do to this water molecule here? Okay, stop looking at them because they're just doing stuff. What is this water molecule going to do to the other water molecule and vice versa? I got some positive stuff. I got some negative stuff. What does positive do to negative? They attract. So the positive attracts the negative. Now, we've talked about attractive forces within particles before, right? So if I have my water molecule and it's attached. I'm going to show the attachment this time. Here's my O and my two H's. What kind of a thing is that attaches the oxygen to the hydrogen? What do we call that? That is a bond. What type of bond is that? It is a covalent bond. And we know it is a covalent bond because hydrogen and oxygen are both what type of element? They're both nonmetals. So covalent bonds are between nonmetals. And what type of particle do we form? Covalent bonds help form molecules. So these three things go together: covalent bonds, nonmetals, molecules. Those three ideas go together. Yes? Now I've got this force that sticks the water to the other water, and that is not a covalent bond. Okay, do you remember anything about covalent bonds? How would I describe the strength of a covalent bond? Covalent bonds are strong, okay? Now, if I boil water, if this is a water molecule and this is a water molecule, my two hands are the two water molecules. If I boil it, they start moving faster and faster and faster and faster and faster and faster until, wah! Yes? They break apart. But we have not broken the covalent bonds, okay? Let's pretend, oh, there we go. There's the hydrogens, hydrogen, hydrogen. Yes, they have not broken off the water, right? What has broken, though, is the force in between this water and the other water. There's a little force, positive attracts negative. That force has broken. Those forces are called intermolecular forces. The word inter, if you go on an international flight, you are traveling in between nations. Yes, you've traveled from France to England. I don't know where you're going, but international, between. So an intermolecular force is a force between molecules. Okay, and the intermolecular forces are not strong, they are weak. That doesn't mean they aren't effective, though, because remember, we have those little water molecules going up to the ions and grabbing them and ripping them off. Yes? So the intermolecular force between the water and the ion is strong enough to rip it away from the rest of the crystal lattice. Okay? Going back here now. Where was it? Oh, no. There we go. All right. Did I miss anything from up here? Covalent bond strong. Covalent bond, that's the attractive force. Those are the intermolecular forces. Did I label that? Yes, we did. Okay, good. We're good. Okay, so we will now go back to 1.3b. There we are. Do you feel like it would be helpful to fill this in together? Or are we good without it? What do you think? So this is on page 43. Should we do it together real quick? Okay. We can make a solution. Page 43. Don't forget the flash. I just forgot the flash. It's okay. We can make a solution by dissolving one substance into another substance. Usually that other substance is water, because it's the most common solvent on Earth. For example, if we pour a small quantity of sugar into 1 liter of water, it begins to dissolve. In order to make a true solution, we need to get all of the sugar molecules to spread out uniformly. Or if you prefer, you could use the word evenly. By stirring the water, we add kinetic energy. To the molecules, causing them to move faster. So they will dissolve more quickly. All of the sugar has now dissolved. That means that all of the sugar molecules have spread out evenly. Or if you prefer, you could say uniformly in 1 liter of water. Food dye is made up of what? Molecules. That must mean, what kind of elements is food dye made out of? Oh, yeah, they will have covalent bonds, and what types of elements will they be made out of? Covalent bonds only form between nonmetals, okay? So the food dye is going to be made of nonmetal elements bonded together covalently. And when we add kinetic energy, which is the energy of motion, watch how these molecules spread out evenly in the liter of water. If you could see molecules of sugar, they would have this same even distribution. Whoa, distribution. Next page. The yellow marbles represent sugar molecules. What holds the sugar molecule to the sugar molecule beside it? No, if you've got sugar, like you don't have to have water for sugar molecules to stick to other sugar molecules. So if I've got a sugar molecule, thank you, and another sugar molecule, why do they stay together and stay solid? What's in between them? Intermolecular forces, yes. The blue marbles represent the water molecules surrounding the sugar. If we add kinetic energy, the energy of motion, to this system, according to the kinetic theory, of matter, all atoms and all molecules are constantly moving. Yes. If enough energy is added to those molecules, they will begin to separate and move freely throughout the volume of water. I hope I got those words correct, but they'll work even if they're not quite what the video said. Okay? After mixing, if you were to draw a line through the center of this picture, you would find that the number of sugar molecules on the left are about the same as the number of sugar molecules on the right. And this is what we mean by even distribution. This happens naturally by the free and random movement of sugar molecules within the 1 liter volume. Is good? Okay. Are we okay? What's happening? Dropping things? Now, I don't like this. I would actually change this up because it says we would call this a homogeneous solution. However, a homogeneous mixture is a solution. So that's almost like saying I have, I don't know, I have some wet water. Like it's almost redundant. Do you know what I mean? Like it doesn't make any sense. You cannot have a heterogeneous solution because a heterogeneous mixture is not a solution. By definition, a solution is a homogeneous mixture. Okay? And that is because all of the sugar molecules are uniformly or evenly distributed in the 1 liter of water. Every solution in chemistry has a solute and a solvent. I don't know why I made it 2 blanks. I should have just made them 1 blank, but I guess I got a little carried away there. The solute, oh my God, I'm spelling it with a Y. Oopsie. Solute is what is dissolved in the solvent. Most of the times in the lab, you will be pouring the solute into the solvent. Water is the most important solvent on Earth. As a matter of fact, water is sometimes called the what kind of solvent? Universal. It is called the universal solvent because water can dissolve more substances than anything else. Not everything will dissolve in water, and many substances dissolve very slowly. I don't know. This seems like this part just seems like we're saying the same thing over and over again. Can we skip this part? Okay, cool. And then that's it. All right. So right now, I'm going to have you guys work on pages 53 through 60. That is 1.3 D, E, and F. That's vocabulary. That's for homework. But I will also put up in the homework all the stuff that are reviews for the quizzes next week. Today's notes? Yeah. Anyone else want a copy of today's notes? Okay, I'll just make a class set. Take a phone call.
This can only be